Welcome everyone to our stats class. Oh, Ada, I want to be outside just like you. I am wearing 2 cardigans and I've got a hot cup of tea. I'm frozen like a popsicle. I'm gonna have to go outside. Maybe at the break of the class, I'll make a transition. All right, let's start with roll. Today is the 23rd. All right, Haley.
Here.
Cole. Maybe Cole is not here today. Zach.
Yo.
Hey there. Savannah. Savannah's not here right now. Eliza.
I'm here.
Bree. Are you there, Bree?
Yeah, I'm here.
Okay, great. Grace.
Here.
Greg, with a D, I think. Isn't it?
Here.
Great. Ashley.
I'm here, sorry.
Great. Kyle.
Hello.
Hello. Saga.
Oh, here.
Ada.
I'm here.
Elizabeth.
Here.
Mary Pat. No. Emily.
Here.
Jenna.
Here.
Olympia, I think, is not here today. She sent me an email. And Daniel.
I'm here.
Okay. And then Savannah, it looks like you're here now. Yes?
You hear me?
Yeah. Oh, now I hear you. Yeah.
Okay. I said
Okay.
something before. I wasn't sure if you heard me.
No, I hadn't. So I'm glad you said something.
Yes.
All right. So the plan for today is we're going to discuss issues around variability. And then we are going to start a lab. We'll get it started, practice a little bit with some fake samples. And then I'll introduce what your lab actually is and what you need to submit for next week. Sound like a plan?
Awesome.
Okay. So let me share my screen. Oh, there it is.
Did you get your hair done?
I did.
It looks super good.
Oh, thank you. You're very sweet. I'm still like figuring out what I think about it. I'm like, bangs, I haven't had that for a long time, but you know, just we're gonna lean into it. It'll be fine. Quick note about next week's class will be fine. Let me just pull up the schedule here. I am going to be out of town on the 7th. So what I'm gonna do is I'm gonna record our lecture, have it be live.
For me.
What's that?
The audio is sort of for me.
So you guys can't hear the audio.
I hear you just fine.
Yeah, me as well.
Anybody else have trouble?
I think it's her connection.
Okay, because the rest of you can hear me okay?
That's probably my connection.
Okay, I'm using my fancy dandy, hi, I'm a radio DJ microphone, which is what was giving me trouble. It wouldn't plug into my one, anyway.
Professor
technical
Wendell,
issues. Yes.
I don't know if you called my name for attendance.
Did I skip you, Greg?
I think so. At least I did not hear my name or wasn't here for it.
I did call Greg, but are there 2 Gregs in our
Yeah,
class?
I heard the Greg. I think that's Greg DeYoung.
The Young, and you're Greg McCade. How did I miss you? Did I miss others? Maybe the sheet is not the most accurate. Hold on, okay, let's do this for a hot second here. Make sure that I'm not missing people. Thank you for bringing that up to my attention, first off. I really appreciate that. I'm just pulling up our roster here. make sure, because I went through. Daniel. Yeah, I don't know what I did there, Greg. I'm so sorry. Did I skip others? Bree, Grace, Greg, Emily, Olympia. I'm very sorry. Okay, but you are here with us.
Yes, I am.
Okay, that's excellent.
That's all right.
Okay, and it looks like we have a question in the chat. Who is that CAB? Hello? Somebody said they got there late. I just don't know who CAB 015.
That's me. I'm sorry. I got here late.
Oh, Cole, but I think, oh, yes, you did. You're right. Okay. Thank you, Cole. Okay. All right. So let's talk about measures of variability, what that looks like, why do we care about it? And then, like I said, we'll introduce the lab as well and talk about that too. So we've got a lot on the agenda. As usual, we are going to set up a time where we have a little break, just so, you know, ease of what we're doing. And then we'll transition at that point into the practice lab. Sound like a plan?
Perfect.
As always, ask questions if anything pops up that you're unsure about. And this is just a little reality check because I've got 3 screens. Can you see my cursor on this
Yes.
screen? Okay, so that's the screen I need to pay attention to. Okie dokie. All right, so measures of variability. The main chapter learning objectives is to explain why we care about variability. Why do we even want to measure it? How do we calculate it? And then how do we interpret those measures of variability? And then within each of those measures, we'll talk about strengths and weaknesses. Just important to have a broader understanding as to what is available in measuring variability, but they all come with somewhat of a pitfall, right? Pros and cons, much like anything else in life. So the whole goal in measuring variability, it really tends on these 2 tenets. So one is central tendency, which we talked about last week. So numbers, again, the concept of central tendency is that there's numbers that will describe or give meaning to what is the average or the norm of a given distribution. So we talked about that normal curve or the bell curve being really tantamount, right? When we're thinking about measures of central tendency, because the bulk is centered around the middle, right? Now, with measures of variability, it looks at how much diversity or how much change or how much variability is seen within a given distribution. Now, can you guys think of why that would be important to know? Why do we care about how diverse a sample is?
It can tell you how many people that it covers. So like if you're talking about like a race thing, if it's, you know, white, African American, Latino, and then so on and so forth. But if it just says white and then other, it doesn't really help.
Totally. Yeah. What would be another example of why we care about variability? Think about in academia, where would you want to see some variability?
Test scores,
Right. Say more about that, Bree.
like where are students like normally testing? Like, are they understanding or having like a better score, or are they not understanding the material on the test? Like, if you need to cover some more stuff or what?
Right. So if I'm giving a test to see what are students understanding on this material, right? Like, do they grasp statistics? And there is 0 variability. All students have earned an F on a test. What conclusion might I draw?
You didn't like teach it in a way that people could understand it.
Right. Or the test that I gave to assess their knowledge was not in line. Now, if I have a lot of variability, in fact, variability that really estimates an average curve or a normal curve, that is a discerning test, right? Because it shows the ones who really studied and really understood got their A's, maybe even a B+. The ones who didn't study at all, never showed up to the class, they earned their F or D, and the bulk of the students, found themselves in the C, maybe B-, D+ range, right? So that would be a more discerning test. The same way that if I'm giving a test and everybody gets an A, that makes students happy, but it's not a very discerning test, right? It doesn't show good variability. So either the test was too easy or the material I'm covering in the class is irrelevant for that group of students because they've mastered it already. So there's quite a bit of information that comes through when we actually do measure variability. So there's two types of measures that can help us kind of discuss this idea of distribution of scores. And the main thing, again, is the larger your sample, the harder it is to glean some meaningful interpretations from it because there's too many, right? So we need to clump them together and do, without having to look at every single score. So you come up with your average, right? Or a measure of central tendency. So we talked about last week, median, mode, and mean. Those are the measures of central tendency that we can use to better understand a distribution. So, so that's a measure of central tendency. Now, a measure of variability says how much does every given score differ from the central tendency or differ from the mean. So how far away are they from the norm? So if we're taking, again, an IQ test example, for instance, and we test somebody and they score so high that we recognize that they are 2 to 3, this would be the language that's used, 2 to 3 standard deviation above the mean. That means here's our average point. That's where most people find themselves. And, on average, the bulk of the sample is going to be within 1 standard deviation away. So we give ourselves a certain number of points plus or minus that central mean, that central score, and that's still considered average. So if you think again about the bell curve, okay, and here I am with my drawings again. Watch out, team. Dr. Woltell's drawing. Okay. Okay. All right, I need to put this back up so I can see what this looks like. All right. So here's our normal curve, right? And this point would be our measure of central tendency. That is our mean or median, whatever. That's usually for, evaluations like this is going to be the mean. So within that, if I'm using IQ, just so you guys know, the mean IQ score is 100 and it has a standard deviation of 15. So if I do this, then I know, and we'll talk about this further this semester. This is probably not a very good range, but I would do a band plus or minus 15. And this highlights the bulk of my sample. They live right here. This is what would be considered the average range. So as soon as I know that measure of variability, I'm able to then take a single score and put it in the context of that. So again, if I am looking at a student who is performing amazingly well and their IQ score is 150, well, now I've just given this context, right? Because I'm saying most people on average score 100. And in fact, I can tell you right now that 85% of the population lives within this first standard deviation. And so the fact that this student is way, way, way over here, probably 3 or 4 standard deviations away from the mean, shows how much he is standing out and how impactful that score really is. So knowing a measure of central tendency gives you one bit of the data to interpret what you're seeing, but knowing the measure of variability gives you the other one, right? If a variability is only of 1 point and somebody scores 5 points above, that's super meaningful. But in this, the example of IQ, if somebody scores 5 points above, that's still within that 1 standard deviation because that measure of variability is 15. So 5 points in that example is not as meaningful. So this is why we start looking at those to really get a better understanding of how things are behaving within a distribution. Questions about that? Is that making sense to people?
Sounds good.
Okay. Again, Kyle, thank you for taking on the voice of this class. Love it. If others of you have questions, please unmute yourselves. If you want to send me a chat, it just is hidden in my screen, so I won't see it right away. So if somebody could just give me, hey, somebody's asking a question, that'd be great. Usually just speak up. That is even easier.
Thanks, Kyle.
Yeah, you guys need to give them. Kyle, what kind of gifts do you want from your classmates? Are you a Starbucks drinker? Are you a pop drinker?
Oh, I love everything.
Everything. And he's easy to boot, you guys. Anything. That's awesome. All right. So here are two different samples. So two professors giving a specific test, right? And you can see the distribution of grades. Here you've got kind of a flatter curve as to the students who received, C- down through F. And you see a similar flattening right here for students who earned an A through a B. But here is the main difference, right? Even though they center around, you can see that it's so this also speaks to the class size. This particular line, you see that's Professor Yamato, I believe, or no, that's Professor Brown, I take it back. Professor Brown hit his or her highest dot, right? Students, the highest grade they were able to earn was a B. And you see the bulk of students earned right around a C, C+. Whereas this Professor Yamato, the highest score was an A, right? So this would be more of your normal distribution, right? It is flatter. Again, very few people got Fs, but some did. And then it increased all the way up to Cs, which is your mean, down to A. Now, Professor Brown here, lowest scores right at a C-. So he doesn't have this tail. So students didn't necessarily fail the class, but no one got an A. So both of the distributions show the same mean. It would be right around a C, right? But when you talk about the variability of score, there's a significant difference here. Because in one class, the variability was really from grade C- to B, whereas the other one was A, oops, daisy, sorry about that, A through F. So again, if you just look at the means, and these two professors are talking to their department head and they're like, well, we gave our exams and our exams showed good reliability because as you see, both of our class earned a mean score of whatever that might be, like 76.4, right? But the story is a little different when in one class, not a single student earned an A. That's tough, right? I don't know. How would you guys feel about that? No one gets an A. Everybody gets a C. There'd be an uprising, I feel. Like, what is this test, right? You need to curve it. So anyway, again, the story is if it could be the same mean, but if there's a different measure of variability, that's going to have a huge impact. Okay, here's an example. Two different graduate programs have an average student age of 25. One university has a greater variability than the other. What does that mean? Someone other than Kyle speak first, and then we'll let him have a turn after. Just gotta preserve his beautiful voice.
Does that just mean that one of the programs has a bigger age range?
Yes, absolutely. That's exactly what it means. It means there's greater variability. So the mean might still be 25, but there's more variability. So maybe you'll have some students who are second career, right? Like learning something totally new that are in their 40s, 50s, or 60s, and maybe a few prodigies. Usually it tends to go the other way though. And then one that's more clustered around 25 with students who completed their bachelor's degree and then headed straight into their graduate studies. So yep, that's exactly what that means. All right. So index of qualitative variation, let's talk about this. So we're gonna go deep here into math. Do not panic. The expectation is not for you to know how to do this exactly, so it'll be okay. What that is, it's a measure of variability that is for nominal variables. So if you're looking at the variability of ethnicity, which actually that was an example earlier in the class, you would want to make meaning of that, right? And nominal variables, it's harder. We talked about this already last week. You can't calculate a mean because there's no values with it. So you need to do something a little bit different. So it's based on the ratio of the total number of differences in the distribution to the max number of possible differences within the same distribution, okay? So if I go back here, I can calculate what are all the possible scores a student could have received, right? That would be the max variability. And then I take the actual variability, which for this professor here, again, Professor Brown, the max variability, it would be just C, and then here, C minus, C, C plus, B minus, and B. So you're looking at really 5 data points. So that's what you would do. And here's what it looks like. This is the index, again, qualitative variation. K is the number of categories. You do 100 squared minus the sum. So this value here is the sum of all squared percentages in the distribution, divided by 100 squared times K, the number of categories, minus 1. Okay, so here's what it looks like. These are the different racial groups. You can see there's white, Latino, Asian, Native American, or Native Hawaiian, or Pacific Islander, or other. So the total number here of different groups, different categories would be 5, right? So there's 5 categories. In Maine, you can see that there's one category that has no representation. So Maine has less variability than, for instance, Hawaii. So let's look at that. So the IQV is a single number that expresses the diversity of a distribution. It ends up ranging from 0 to 1, because again, you're dividing it by 100 squared anyway, that's the math of it. An IQV of 0 would indicate that the distribution has no diversity at all, meaning all the cases are found in one category, okay? So if in our class, 100% of the students were sophomores, I would have no diversity in terms of the grade or the level that you guys were in terms of college level. And then the IQV would be 0 because there's no diversity. An IQV of 1 would indicate that the distribution is maximally diverse. So with our example, again, we know that there's, we're going to say for the sake of argument, 4 levels in college: freshman, sophomore, junior, senior. If I had students from each level represented, the IQV would be 1 because the class, all cases in the distribution are evenly distributed across categories. There's some students in each of the categories, which shows diversity. Okay, so this is what this would look like. I would take the percentages, right? So let's go back here just for a second. This here is out of 100. So these are my percentage scores already, okay? So I take that, these again are the same values as we had in the other table, and I do the percentage squared, okay? Which will give me this total score. Next, I plug it into the formula, okay? K is the total number of groups that have representation. So remember, Maine only had 4. They didn't have Pacific Islanders, whereas Hawaii did. So they have the 5 here. And then you take their total score, right? That's the total percentage score that we had here at the bottom. And then minus the total categories, again, that were highlighted. So again, Maine only has 4, whereas Hawaii has 5. So you see here, the diversity, the IQV, the index of qualitative variation for Maine is 0.07 versus Hawaii, which is 0.84. What do those numbers mean?
Can I ask a quick question?
Yeah.
So we do not have to be able to recreate these the tests?
I don't think you'll need, no, you won't need to do the math part of that, but you need to understand the value. So if I say a group has an IQV of 0.7, what does that mean in terms of the diversity?
There's less diversity than Hawaii.
Yes, very good, Greg. Let's take it one step further. So comparatively, Maine has less diversity than Hawaii, but just singularly, how about Maine?
Maine is not very diverse.
No. Right, so the closer we get to 0, the closer it is that all numbers are found in one category. And we know this because look at this, 97.3% are white. So even though they have some representation in 4 categories, it is very minimal in the other 3. Whereas just looking at this, again, eyeballing it, you see it's far more diverse in Hawaii. And we know this also because the closer you approach 1 with your IQV, the more diverse it is. Does that make sense?
So would it be like a
Yeah.
percent, like 7%, or is it just a 0.07?
No, it's just a value. That's a very good question. This is not a percentages. This is a value. It's an index.
Only because like the range honestly is from 0 to 1 though, right?
Exactly.
That's why. Okay.
Yep. Much like when we talk about reliability and correlation, how well two things are correlated, those values only range from -1 to 1. So it's never going to be a percentage. It's just how far does it go in there. And with that too, like the closer you are to 0, that means there is no relationship. So with this, there is no diversity at 0. So we're really, really close to 0 with 0.07, right? Okay. All right. So these are the steps that you would do to calculate it on your own. You would construct a percentage distribution. You would square the percentages, sum them, and then calculate the IQV using this formula. It's not meant to be complicated. It's just meant to give you an idea of what it's the calculation of it. Okay. All right. So again, with this, we could do the exact same percentages for the purposes of this class. We don't need to worry about that as much, but you can see these are the different regions, right? Northeast, Midwest, South, and West, and the breakdown here in race. And then here's the quotient, the index of qualitative variability. So what do we see? Which of these regions is most diverse?
The West.
The West is most diverse. Yep. Which is the least?
Midwest.
Midwest. Wah wah. We're not doing a good job. This is as of 2011. It's fine. All right. What is a range? That is another measure of variability. A range looks specifically for interval ratio variables that will not work with nominal variables. It's the difference between the highest and the lowest scores within one given distribution. So it can be calculated by percentages as well, but it is a very crude measure. High and low scores, we need to be mindful of that, right? Like same with the mean. With a mean, we can have outliers. There can be really high scores and really low scores that are not really representative of the rest of the distribution. So we need to be cautious about that. So it can be at times misleading as to how diverse a distribution is, because everybody can be clumped around the middle and then you have 2 outliers, right? And those would be included in a range. But if it's an N of 1, that's not really representative of the entire distribution. A different measure of variation is interquartile range. Okay, so it looks again at interval ratio data and it indicates the width of the middle 50% of the distribution. And it's usually defined as the differences between the lower and the upper quartile. So much like I did on this graph, let me make another one. Okay, so if I was dividing it, okay, I've got a normal distribution, and now I'm going to be dividing it in quarters. It's looking at the difference between the upper, well, this is the lower and upper quarters, like this section that has the bulk of the people in the distribution. Okay, so again, you're taking quartile 3 minus quartile 1, or the 75th percentile minus the 25th percentile to get a calculation as to this interquartile range. So looking at this, this is the range versus the interquartile range as expressed in number of children among 2 groups of women, okay? So this is the number of children that they have. The most number is 10, smallest number is 0. So the range would be 10 minus 0, range is 10, okay? The interquartile range, though, would be figuring out the quartile 3, which is 3 kiddos here, and quartile 1, which is 1, and that would be 3 minus 1, the range is 2, okay? Now let's look at this again. This is the same thing, 10 minus 0, that would be a range of 10, but this one, it is more diverse, right? This is not very diverse. This is more diverse, so if we're looking at this, it's 6 minus 2, or is that right? No, 6 minus 1, sorry about that, shows then a interquartile range of 5. So this is far more meaningful because otherwise the range would show that it's super diverse, right? Range is at the optimal highest level. There's 10 possible categories, you got a score of 10. But is it actually reflective of the distribution? Not really. And you can see the interquartile range gives you a bit more data. The lower the number, the less variable it is. So the interquartile range of 2 shows that it's really clumped, right? It's clumped towards 0 kids to 3 kids, and then there's a couple outliers. Whereas this here shows more variability. So again, a quartile range of 5.
Not to interrupt, but so why is the third quartile on the right side on 6? Like, what makes it where it's not on the third as well? Because they're the same number of, like, does that make sense? Like,
totally makes sense. And
okay.
if there was only, so you see these little drawings of women here?
Yeah.
That's the frequency. So
Okay.
there's 1, so this is the same here. There's 1 right here. That's why quartile 1 is the same, because these scores are the same. But as soon as you get down here, they vary. So you've got 3 and 3. So the first third has these 4 together. And then the second
Okay.
quartile. So you're having to divide up, kind of what I was trying to show with this, like you're dividing up your sample, your distribution equally. So it's based on the frequency.
Okay.
So because of that, yeah, does that make a little bit more sense?
No, everything clicked. Yep, thank you.
Okay, so that's why this quartile ends up being further, which that's the whole point, right? We want to go to the 75th percentile, see what is the third quartile, because that gives us more data because we're organizing again the frequency. Yeah, there's another example in your text about that, the interquartile ratios. Okay, here's another way we can do this. Some of this might be like an old refresher back from maybe middle school stats and math, but a box plot. And I say this because my daughter did that last year. I was like, oh, you're doing a box plot. You're doing stats. She's like, I hate it. It's like, you're not allowed to hate stats in this house. I'm sorry. You're born to the wrong house. So what is a box plot? It is a graphic device that usually presents the following pieces of information. It'll include a range, the interquartile ratio, the median, each quartile, and the minimum and max value. Because obviously as soon as you have the range, you have the minimum and max. So this is what it looks like. So you could see through here, you've got your max and your minimum. Your median is right there in the middle of the box, and then it'll identify the first and third quartile. This value ends up being your interquartile range, right? And then this is your actual range because you're taking your max and min. Now, this is a very standard picture of a box plot. They never look that even. They usually look more something like this, because it'll highlight if you have any sort of skew in your distribution or outliers. So this is the distribution of the projected percentages increase in the elderly population for a given number of years. So the highest value here is in Alaska, lowest is in Washington, D.C. From that, we can calculate a range, right? Because we take 50 minus, this would be negative 14, but that's all right. Median is 18.8. And then we could see here our quartile for the first and third. So this is based on the percentage increase in the population. So when the box is skewed, the box and the median, right, this line, it's not centered. So see how this box is not right in the middle? It's closer to this bottom because that's the way it's pushing out. So there's more lower percentages, which leads us to a positive skew. So again, if you're imagining that graph, like I was showing you guys, if you have more scores that are at the bottom, that kind of ends up making a sideways P, that's a positive skew. Okay. Then variance, what is just variance as a whole? That the whole word, isn't it? So it's a measure of variation for interval ratio variables again. It's the average of the squared deviations from the mean. Now this you will need to know how to calculate by hand. It tells us on average how much do individual scores deviate from the mean, just like I was describing earlier with IQ. it's based on all of the scores, not just two, like the interquartile range, right? Which just looked at the two, the 25th and the 75th percentile. Okay, so let's see how we're gonna do that. I'm gonna throw down some math. You will need to know these formulas. Again, every test you're gonna take in this class, you're gonna have access to your notes, so just to make sure they're clear from there. So here's how we're gonna do it. The way we calculate it is that it's the average of each score's squared difference from the mean. When I write it out, it never seems to make sense. You're about to see it in a second, it'll click. So here are the steps you need to do. So first you need to subtract the mean from each score. So you have your individual score, you have to subtract the mean from it. You're gonna square those deviation scores. You're gonna add up all of them, and you're gonna divide it by the sum squared deviation by the number of scores. Okay, I've just said a lot of nonsense. I'm sure all of you are like, this is where I'm gonna fail stats. It's not. Here it is. This is what it looks like. So this is your individual score minus your mean score. You square that, right? Here's the square. You're squaring the variance, and you're summing it. So it's the sum of the squared deviation from the mean. So big word just to say you're summing all of that, and you're dividing it by the total number of scores, either -1 or the total number of scores, just your plain N. We will talk about the difference between the two, sample versus population. Okay. So we are gonna follow these exact steps. We're gonna calculate the mean, right? So did I have that over here? No. Calculate the mean, which we know how to do, right? You're summing all of your scores in a particular sample, dividing it by the total number of scores. That's your mean. Then you're gonna subtract each score from the mean, square the deviation, sum it, and then you're gonna divide the sum by n minus 1, and the answer will be your variance. So we're gonna work through a couple of examples. I kind of want to jump to that real fast. Okay. I take it back. We're not gonna jump to that yet. I'm gonna tell you a lot about what they look like. So just tuck that into your back pocket. That is how we calculate variance. These are some examples of distributions. Again, you'll have the same mean, but different amount of spread or variation. So notice all of these, the mean is the same thing, but the actual distribution of score is very, very different, okay? So the mean here, 3.2 all the way across, this would be more of a normal distribution, right? Whereas this is more of a bimodal distribution, and this is a very negatively skewed distribution. So again, the mean is all the same, but the spread looks different. So we're flipping it on its head. All of these examples are a different mean, but it's the same level of spread. So you see that they're all about the same flatness, right? The same kind of distribution. So they would have a very similar variance, but the means are different. Okay. Again, this is an example of two distribution with the same mean but different amount of spread. So housing prices and different neighborhoods. So this is a neighborhood with consistent type of housing, all single family homes, for instance. So that would give you the mean, and here's the spread, right? Pretty average, common, normal distribution. And this is the prices of home. This is the mean. Again, same exact mean, but for a neighborhood that has different types of housing situations. So maybe you have single family homes and condos and apartments, right? So then you're gonna have some that are lower in price, and especially if there's a lot of them, some that are maybe some real expensive condos. It just depends. Okay, so I want us to go back to something real quick. This formula is for variance. That's how much your sample, your distribution varies. The way we're gonna report that variance is talking about the standard deviation, which will give you an exact score. So it's again a measure of variation using interval ratio variables. It is the same thing as the variance, except we're gonna do a square root of it. So that same formula that we looked at, just hop on a square root right on top of it. So it is on average how much scores differ from the mean in either direction. So like I was saying before, if I know my central tendency value, I'm able to add and subtract the standard deviation number to know where the bulk of my people should lie, right? So it'll show me how much it deviates from the mean. The thing we need to keep in mind is that a standard deviation does not describe the shape of the distribution. All it does is tell you the different brackets where you will find scores. Okay, so here's some possible distributions for family size in a country where the mean is 4 and the standard deviation is 1. Okay, mean is 4, standard deviation is 1. The reason why it's 1 is you can see here, those are it's 1 points, right? Like, so it's 1 away from the mean. So that's why you see 5, 6, 7. 5 is 1 standard deviation away, 6 is 2, right? Okay. The whole point of this is to show these all have the same mean and the same standard deviation, but the distribution varies a very great deal, okay? So once you have those two pieces of data, mean and standard deviation, you don't necessarily have a full picture of what's going on with your distribution. That's the main point. Okay. So variance, as we were talking about earlier, is very rarely reported in articles. Standard deviation is used as well. And luckily, the formulas are very, very similar, like I was saying. It's the most common way to describe the spread in a group of scores. And what you do is you calculate the variance, just like I showed earlier, and you take the square root of it. And that gives you the standard deviation. Unlike the variance, which is really specific to each unit of measurement that you're taking, no matter, depending on what you're calculating in your sample, the standard deviation is the same units as the individual scores. So in a normal distribution, 34% of scores fall 1 standard deviation above, and 34% of scores fall 1 standard deviation below the mean. So if you add that up, this idea here that I talked about, now this is key. This is in a normal distribution. Okay, let's see if we're understanding this concept. So in a normal distribution, here's my mean, standard deviation below, standard deviation above. So if I asked you, what percentage of the population fell in this group, 1 standard deviation above and below the mean in a normal distribution?
68.
68, very good. How'd you figure that out, Greg?
Well, 34% fall above and 34% fall below. So that is a total of 64% of the population.
68, you got it, that you're spot on. So that's exactly right. So when you have a normal distribution, that's the key word. If it's not a normal distribution, this does not apply. But 1 standard deviation above, 1 standard deviation below, you have 68% of your population, which means, let's do some quick math. What is left over?
32.
Okay, 32. And is that 32% are above or 32% are below?
Total, so it's 16% are above and 16% are below.
Exactly right. So now we're really talking about these tails, right? If I'm figuring out that really 16% is below, 16% is above. So again, think about things you've heard where it's like, well, he scored 3 standard deviation above the mean. That gives you a sense of how small of a percentage that is, the likelihood of that happening, right? This is somebody who's well above what would be expected. Okay, or below, depending on what your example is. Okay, so let's go back to the math part. Let's stretch it out. We can do this. This is the same exact formula as we saw earlier for variance. The only thing we did is we added the square root. Okay, so this is the computation to get a sample standard deviation. This is why we're doing n-1. Little secret here, folks, we are almost 99.9% going to be using a sample, because how often do we use an entire population? Very rare, right? If I was calculating the mean age for and standard deviation of the census of the United States, yes, that would be a population, but very rarely do we do that. We usually speak in means. And the reason why we do that is because it's more efficient. You don't need as many people to actually do the calculation, and you're approximating what the actual score would be if it was a population. So you're still getting close. Okay, so for the purpose of this course, this right here, this is the formula that you want to jot down and have be handy. And we'll talk about how to calculate that. I use a table. I find that works best. So this is different types of deviations from the mean. If our mean is 19.95, we can see here how much these particular scores deviate from the mean, right? This is just another illustration to show deviation. Okay. Percentage of change, again, in the elderly population. So we have our score. This is the different regions. So the Northeast is expecting 16% change, the South 22.8%, Midwest 14%, and the West 27%. First thing I want to do is I want to calculate what? What is this calculation here?
Mean.
The mean. So the way I do that is I add all of these up. I was saying percentages, but yeah, anyway. Add these up. That gives you a total of 79.8. I divide it by the total number of categories. My N is 4, right? So that gives me a mean of 19.95. So 19.95% is on average the percentage change in the elderly population by region. Okay? Okay, first off, any questions about that? Because we covered the mean last week, but does it make sense still? Because if we're not understanding the mean, I don't want us to move forward to standard deviation. They're just going to get people confused. Any questions about that, the mean? I'm thinking no. Okay, next step. And this is why I think doing it as a table is most helpful. So honestly, the way I would do it, and I'm just going to doodle here because this is what I'm going to do. I would figure out whatever this is and then do my mean. And then, okay. Sum. Oh gosh, you guys have such bad handwriting. But this is the kind of table that I would always have for a calculation of standard deviation. First, you're going to need to have your actual values, right? What are the actual values? And then at the bottom, calculate your mean. Then you're going to have a column that says your actual score minus the mean. The next column is the score minus the mean, whatever this value is, squared. And then at the bottom, you're going to do the sum of those. So let's take it step by step here so we know what we're doing. So I've identified that my mean is 19.5. Now I'm going to take it away from each of those values. So first I'm going to do 16 minus 19.5. That equals negative 3.95. Do I worry about the fact that it's a negative?
No.
Why?
Because it shows that it's a negative. It's below the standard deviation, below the average.
It's below the average, right? And if I think about all the distribution, I can have a mean, right? What's my middle score? But there's definitely going to be scores that are below the mean. So it makes sense that there's a value that would be negative. The other reason why I don't need to worry about it is we're about to do what to this value? We're about to square it.
Yeah.
So it's not going to matter a whole lot. Okay. So I go through one by one the difference between each, and then I can sum here the difference between my scores and the mean. Why would this be 0? It's not meant to be tricky. But if we figured out our measure of central tendency, we have our mean, and we say you are this far away from this number, and you're this far away from this number, and we add up all those differences, that's going to come back to be exactly the middle number. It'll be 0. Okay, more on that in a minute. Okay, so here's just an illustration of what we just described. So the mean is right here, 39.46. the standard deviation would be 7.8. So this shows again how much variability there is within my distribution. This one, quite a bit of variability. Down here, my mean 39.87, almost the same. This again, looking at age, but the standard deviation is 3.75, much tighter. It's a more closely knit group. So again, you can see the difference. The standard deviation score speaks a little bit to the variance, right? It shows you how diverse it ends up being. Okay. Oh, gosh, what just happened? I was trying to, oh, I'm doing it again. I don't know why I'm clicking. This is the mean and standard deviation in research articles. This is another one. You would go through here, you'd figure it out. This is very common in research articles. It'll be reported this way. You'll have a mean and a standard deviation for each of these. So you need to understand a bit, like, what is it they're telling me? Why do I care about that? Well, a mean is important, and a standard deviation is, again, how much does it vary away from your central tendency? So you can start having a better grasp, again, on how much variability there is. So if you click here, affiliation Q displays, leaning toward partner, the standard deviation is 20. So that means each data point is really far spread apart. Whereas this one, gesticulation, is really, really, really tight, right? Really, really close. Okay. So when we talk about variability and choosing the correct measure, we want to know first what type of variable it's going to be. Is it going to be nominal, ordinal, or interval ratio? Because that's really going to matter. The only time you're going to use that IQV, the interval quartile, that's not right. I'm even forgetting it. No. But anyway, the only time you're going to use that is going to be for nominal variable. So again, ethnic group, religious groups, things like that, things you don't have a number for it. The rest of the time, you're going to be using really standard deviation is going to be the biggest piece. We'll talk about standard error of the mean in a future class as well. Okay, so what I'd like to spend the rest of the class time doing is going through 2 or 3 of those examples as a class, and then I want to introduce the lab as well so that you guys know how to do it. I'm going to have you guys do it both ways, creating a table and also running the stats within Excel so that you know how to do it quickly. As soon as you know how to do it quickly, you'll probably want to shake your fist at me for doing it the long way, but I think there's some value in understanding how we get to it. So for the purpose of break, let's come back. How about 3:10? Let's come back at 3:10. We're going to practice everything we've just learned and then work on the lab. Sound like a plan?
Perfect.
Okay. All right. Come back at 3:10. See you guys soon.
Thank you.